Hi everyone. It's been a while since I've been in a room with that many people actually. So none of the usual suspects are here today, so I'm afraid you're stuck with me for the OpenCL working group update. Those are not my slides, so apologies in advance for any hiccups or pauses. And with all those disclaimers out of the way, let's get started. So Khronos, I don't think we really need to introduce Khronos anymore to this audience. Standards body looking after many open standards with dozens of companies contributing. It's been going on for 20 years. I think everybody has found that very useful and productive. Trying to get them. Yeah. So a quick summary maybe of the compute acceleration standards that Khronos looks after. Starting maybe from OpenCL at the bottom right corner, that most people probably know here. Once again, 10 years of history in constant evolution and targeting a wide range of devices, CPUs, GPUs, FPGAs, and maybe more recently, more creative types of hardware. In addition to OpenCL, we've seen an uptake in the use of Vulkan as a compute API also recently. So it started life as a graphics API in 2015, something like that, and has been steadily incorporating more and more compute features since, and to the point that we'll come back to that, OpenCL and Vulkan are becoming actually fairly close in terms of capabilities. Built often on top of that, we have SYCL that historically was built on top of OpenCL. That provides a single source C++ programming model for compute accelerators. We also have OpenVX that specializes in vision problems and inferencing, neural network inferencing. So a fairly rich ecosystem of standards. In terms of application libraries and engines using OpenCL, as you can see, there's no shortage of them, really. I won't go through any of those, but I think the volume speaks for itself, really. And OpenCL has been the most pervasive cross-vendor compute standard. So in terms of where we are today and what's new, here are the highlights that the working group wanted to present. OpenCL 3.0 adoption is going strong, actually after the slight lack of interest that we've seen with 2.0. We pivoted, as we've already talked about in previous conferences, to 3.0 that offers a more flexible set of features. Not all features are mandatory, and implementers get more choice to pick what they want to support. And that's served us pretty well. We now have about 14 OpenCL 3 adopters, and that's only second to OpenCL 1.2, and probably likely to overtake 1.2 at some point. And I know as a friendly competition with our Vulkan friends, it seems we've now overtaken Vulkan. So around OpenCL, we're seeing significant open source activity with Rusticle that we'll hear a lot more about tomorrow. Clang LLVM as well, that is becoming more and more active and spanning a wider range of compute projects, really. Layered implementations are a big topic as well. We'll come back to that a bit more with CLSPV, Ankle, OpenCL on 12. And OpenCL, we're seeing, is becoming a very popular substrate for the higher model levels. We've seen SYCL for a number of years now. We also see that people are using it to implement HIP, and there are some people in the room you can ask questions to. So yeah, great low-level API that enables a lot more stacks to be built on top. We're also seeing as a trend the rise of layered implementations of OpenCL. I have a dedicated slide a bit later, especially over Vulkan, where there's quite a bit of variety here. And some of these are already deployed in production today in machine learning use cases. And I think it's pretty clear that people still like the programming model of OpenCL, even when they don't have access to native OpenCL implementation. And that's why layering, we think, is going to become popular. And related to that, we've hit the first interesting milestone, which is our first conformant layered OpenCL 3.0 implementation. So the quarterly releases of the specification and ecosystem artifacts of the loader, headers, layers, and all of that are still going strong. And we just released 3.0.16 before the conference with the final version of the external memory and semaphore extensions. We also transitioned the specification to a new unified format. So historically, the extension specification, core specification, language specifications were all separate documents. And we're starting to reach the point where this was becoming a problem. There are some extensions that need to alter text from the core specification, and that makes for an extension document that looks like, take this paragraph and replace it with this paragraph. And if you start layering these on top of each other, it becomes a bit of a mess. And it's hard to refer, hard to use for application writers. So we're making steps toward a unified specification that has everything in one document and notes that tell you what is available when a specific extension is supported. There's a fairly active extension pipeline as well, driven by mobile, embedded, and desktop markets. And I'll come back to those a bit later, but we've seen extensions for recordable command buffers. There's work ongoing around cooperative matrix support or unified shared memory, YUV images, and image tiling control. There's a fairly long list of these, but at least are being worked on. So that's the adoption story on a graph with a history of a number of adapters over time. You've got the logos of the various companies that have implemented OpenCL 3 with a green tick mark next to their name when they have submitted conformance. Bit of a view of how OpenCL is trending on GitHub. So with a usual disclaimer that we don't really know what this means, but we see the number of projects that tag OpenCL increasing fairly regularly and actually faster and faster. Inflection on 2020 on that curve. But whether it is that people clone more projects or many applications are being developed against OpenCL, it's hard to tell from that stat alone. Another highlighting was the addition of OpenCL support to GPUinfo.org. So for those who are not familiar with the website, it is a directory of OpenGL, Vulkan, and now OpenCL implementations that list also the specific features and extensions that the implementations support. So very useful to get an overview of how widely a given extension is supported. So if as an application writer, you want to know how much of an install base am I going to target if I require a given extension in my application, this is the place to go. There is an application that enables anyone to submit a report. So if you have a device that you think is not represented, feel free to make a submission to the website. It's useful to implementers, application writers, and library developers as well. So those who are familiar with the conference probably have seen a version of that slide. This is our attempt at capturing the entire ecosystem in one slide. We systematically fail to highlight everything. There's just way too much to pack on a slide, but those are the highlighter. I won't go through it. We could spend an entire hour talking all those projects, and it's very, very partial. We always feel it misses too much, but it gives, if anything, a good overview of the richness of the ecosystem and a number of projects that interconnect together. Now, layering. So this is an interesting trend and one that I think will stay with us for a fairly long time. So layering is the idea that you implement one standard on top of another. And as you can see from this matrix, there are quite a few combinations that are supported today. And talking about specifically OpenCL, because that's the one that interests us the most, there's a good richness of projects around layering. We've got an implementation of OpenCL around on top of DirectX 12. We've got several on top of Vulkan, and I'll come back to that. And this is useful for a number of reasons, really. There are scenarios in which an application wants to target a specific API that a vendor does not support natively, or in which we want to provide better interop between multiple APIs that are implemented on top of another one, potentially. There are many, many reasons for which layering is interesting. And a lot of the people who invest in applications tend to not want to rewrite them once the trends change or the critical mass maybe of implementers shifts towards a different standard. So that enables us to retain existing investments, and those bridges are very valuable for everyone, really. Talking a bit more about OpenCL layered implementations, we have selected a few here. There are some more, but they're maybe a bit less prominent. So starting from the left, we've got the CLSPV CLVK pair, which is the first one that reached the conformance milestone, mostly driven by the Chrome OS guys these days. So CLSPV, I believe, has been presented a few times here. It's an LLVM-based compiler for OpenCL and C++ for OpenCL that targets Vulkan SPIR-V. And CLVK is, well, has been a prototype runtime for quite a while now. I think we've removed prototype from the name because it's starting to be deployed in a number of places. So the idea is you link against that, and you just run your unmodified OpenCL application on top of a Vulkan implementation. The next one that is seeing quite a bit of activity is the CLSPV plus ANCL pair. So this is same compiler, but a different runtime that is implemented in the Angle code base. For those familiar with, or not familiar with Angle, rather, it's an implementation of OpenGL on top of Vulkan. So this is mostly driven by Samsung, and we have Hello in the room if you want to ask questions. Mostly aiming at Android, I think, at the moment, with the ability to provide, obviously, very good OpenGL, OpenCL interop. The next one would be Rusticle over Zinc. So using the Rusticle frontend to Mesa and the Zinc backend together, that gives you an OpenCL over Vulkan implementation. And I'm sure Carol and others will be happy to talk a bit more about that. And the last one then that we've highlighted here is Microsoft's OpenCL on 12. So an implementation of OpenCL 3.0, I think it is these days, on top of DirectX 12. OpenCL and machine learning. We had quite a few discussions as to what we should present here. And I think the summary is that there's a very rich ecosystem once again, and we're seeing many uses of OpenCL in machine learning stacks, many different paths, and too many, maybe. What else? I think the list once again speaks for itself, and I'm not sure I want to single out any one of those frameworks really. But I think what this proves is that OpenCL has proven a very successful target for many of those frameworks. It's a prime way of accessing GPU compute in many scenarios. Moving on to the recent specification release. So as I said a bit earlier, we released 3.0.16 on the 4th of April. So in line with our regular quarterly cadence. And that's got the usual mix of new functionality and bug fixes. Some of the highlights, maybe in terms of new extensions, we've got the kernel clock provisional extension. So this enables you to time critical sections within a kernel. You can sample a clock and sample it a bit later, and you know how much time you spent in a given loop, with many caveats, as you might imagine, when it comes to time measurement on a parallel device. But this is the first provisional release of the extension, so we'd really appreciate any and all feedback really on it. And secondly, the external memory object and semaphore extensions have now been finalized. So they were released provisionally. Can't remember, was it last year or maybe even a bit before that. And we think we've worked out enough of the kinks now to call them final. And as I said a bit earlier, we have a fairly healthy pipeline of new extensions being either discussed or in advanced stages of development. Maybe worth highlighting also that we're seeing a few more EXT extensions. So those are unratified and often developed in public. And I'll maybe come back a bit to that as well. But there are notably a few image-related extensions that are being developed on GitHub. So if you go to Khronos Group OpenCL docs, you've got the draft specification and all the discussion is happening in public. And we're finding this is, in some cases, a very useful model to develop new extensions. What more can I say on this pipeline? Unified shared memory is going to be a big topic probably for the group over the next year. Some more extensions around the subgroup size control. So as you know, today, if you don't really know the size of a subgroup, and you certainly can't get any way of you don't get any way of requesting a particular size, and yet some subgroup algorithms have to be written for a specific subgroup size. So this is something we're looking to address. There's quite a few extensions around images as well. Probably come back to those a bit later in our presentation. Support for the so-called cooperative matrix programming model as well. So this is the idea that you can get multiple invocations or threads collaboratively computing small matrix products, and it's obviously very useful to accelerate machine learning and many other of those algorithms. Timeline semaphores can help in some scenarios where the usual binary semaphores are not that suitable to set up synchronization between multiple entities in a system. I'm trying to purposely not go too deep into it because it would take too much time. Then support for longer vectors as well. We found that some vendors are interested in offering support for vectors of 32 or 64 elements, and they think that they can provide a performance advantage with that. Support for indirect dispatch as well. This is the idea that you can enqueue a kernel, but not specifying the size of the ND range at enqueue time. And that size can come from a buffer later on. So you could compute it from a previous kernel, for example. And ML operations, finally, there are lots of discussions around that, but I don't think any obvious direction or proposal that we want to talk about at this point. The SDK also is still ticking along fairly nicely with new samples and new integration and utilities being added fairly regularly. There have been multiple projects around that. I'm not super familiar with the details myself, so I'll avoid saying something that's wrong. Thank you. I have only 5 minutes left. What else could I say on the SDK? I think that's about it. Discussion topics. So these are some of the items that we thought could be interesting to have as a corridor discussions or encourage people to talk about that. How can we reduce desktop fragmentation? So this is still a problem, we think, for OpenCL. There's the question of how we can ingest SPIR-V, maybe a path that would help people would be to integrate it into LLVM. So you would get a SPIR-V consumer directly in LLVM. Layered implementations could help here, or other more open implementations. Once again, I'm thinking of RustyCL here, and I'll encourage you to attend tomorrow's presentation. How can we encourage layered implementations as well? All of them, really. Question over whether RustyCL over Zinc over Molten VK provides a viable path to supporting OpenCL on Apple devices. And I think the answer is yes, actually. We have seen some anecdotal evidence that people have been successful now with getting this to work. Maybe I'll add one question at the back of that. How much layering is too much layering, maybe? that starts to be a lot at this point. OpenCL and Raspberry Pi is something that a lot of people are interested in as well. How can we foster better uptake of OpenCL directly in some of the major machine learning frameworks? So TensorFlow and PyTorch being two examples here. They don't really have direct OpenCL backends, and that's something we're wondering whether this needs changed. TVM is a project that a lot of people are interested in as well. And once again, what extensions or support do we need to provide in OpenCL to make this easier for people to integrate, or to make OpenCL a more compelling target for those frameworks? And listed again the same extensions. How can we increase the effectiveness of OpenCL as a substrate for some of the higher level models, so SYCL and OpenMP? And last but not least, do we need a safety critical version of OpenCL? We'll hear a bit more about a safety critical version of SYCL, and traditionally based on top of OpenCL. Does it mean that we will need a safety critical version of OpenCL? And we know some are thinking or working on that. So on all those topics and all the others that are not listed here, your feedback is more than welcome, and we would love to hear what you have to say, or any problems that you might think that you think we're not aware of. And there's one tool that we think could be very useful for that, and that we feel is a bit underused today, and that's the OpenCL advisory panel. So that is a middle ground between the working group and external entities. So for folks who can't join the working group for whatever reason, but still want to get an advanced view of what's happening in the working group, give feedback on proposals, the advisory panel, you just need to sign an NDA, and then you get access to some of the proposals that the working group can circulate to the advisory panel. Give us feedback. So it's a good way of participating in the development of upcoming extensions. If you're interested in that, you can reach out to the email that's on screen. And yes, once again, feedback is more than welcome. And if there are problems you see or things that you think we're not getting right, we need to know about it. You can raise issues on GitHub directly, contact the email that's on screen, or use your contacts maybe. And I'll go through that. That's a usual list of pointers for those who want to learn a bit more about what was mentioned today. And that's all we have, I think, for... Yep, that's the last one. Any... Thank you. Okay. Any questions from anyone?
Oh, I think adopters means people that have implemented the OpenCL specification for their hardware devices. Is that?
It's not quite the definition, actually. It's people who have registered it with Khronos. So there can be implementations and official adopt.
Maybe one small quick question, I guess. When you mentioned the frameworks, you explicit in TV.
Yes, it's common. I think it is on our giant everything in one slide as a path that we are interested in.
Okay.
Yes.
Okay. And I'm trying to understand, was there any OpenCL backend for MLIR as it stands today, or not really?
Not quite, actually. So MLIR supports SPIR-V, but today most of the uses we've seen of that are for the Vulkan flavor of SPIR-V. And conversely, the LVM backend that's in SPIR-V backend that's in LVM is mostly targeting the OpenCL flavor of SPIR-V.
Okay, got it. Okay.
All combinations in that matrix will be interesting for a variety of.
Got it. Yeah, thank you.